So in an email I sent out yesterday, I outlined the details of the exam, and basically it will be like all of our other exams. That is, there will be a strict time limit. The final exam is 2 hours long, and I'll add on 5 minutes at the end to give you time to upload your solutions. No calculator. Show your work always, more important than your final answer, and no calculator. The arithmetic will be straightforward or unnecessary. Just like on previous exams, you should be expected to find an integral that gets us something and maybe not evaluate it. So read each problem carefully, identify exactly what I'm asking you to do, and then do that, and don't do anything more. Also in the email, I mentioned that I want you to have a camera. So we'll all check into Zoom at the beginning of the exam, and that way I can watch what's going on. All right, so the topics. It will be cumulative, although not every topic that we've covered will be included on the exam. So I have an outline on the board. Well, these are the topics that possibly could be on the exam. Of course, the new material we've covered in chapter 11, we've done the first 3 sections. The first section is parametric equations. And I've identified kind of the main ideas there, the basics, what's going on with parametric, how's it different from what we've already know how to do. And then we did 2 calculus applications, slope of the tangent and the arc length, the length of a curve defined parametrically. We have a nice formula. I didn't write it here. It should be fresh on your minds. I think part of the basics up there, which the homework had us work on, is this idea of elimination of parameters to find a way to navigate between parametric equations that we're learning and things that we've learned in the past. All right, and then we had 2 sections on polar coordinates. We had a section that covered the basics. How do we identify a point in the plane in terms of its polar coordinates? There were some very important conversion formulas there, super handy to know. Those are always true. It's how we move from one system to the other or back, whichever way we feel like we need to go. And then our focus eventually was on polar functions, and we always think of r as a function of theta. Never ever do we think of theta as a function of r. And when r is a function of theta, we can picture our curve sort of moving around the pole, around the origin. As theta increases, r changes, r measures the distance a point is from the origin. And so we kind of get that picture. Instead of in rectangular, a curve flowing from left to right, a function, or from maybe bottom to top, these guys flow around the pole as theta increases. And so we can get things like spirals, functions whose graph are spirals that we really couldn't get using rectangular functions. All right, that's the new material. Wait, there is a little bit more new material. I'll put it on the next board. I should have put it here, but I'll be sure and get it. There's our area formula for polar coordinates. The only calculus application we did was area, and it's not really very intuitive. We think of the integrating functions to get area, but because when we're in polar coordinates, it's a little bit different. But we do have a formula. There it is. All right, so previous topics that may, underline may. In a minute, when I finish this, I'll tell you some topics that absolutely will not be on the exam to help you focus your study. So we started this semester off talking about area between curves. And, I think in here, these curves would be rectangular, defined curves in terms of x and y, maybe functions. And we know to get area between them, we need to integrate. We just extended the idea of area from Calc 1 into Calc 2 to talk about between curves. And then spend a lot of time on volumes. And notice I said you need to know one technique. I intend to ask a question. If there is a volume question on the exam, there may not be. But if there is, like either method will work. You can get all the points if you know everything about disc and washers and nothing about the shell method, or vice versa. That is, if you really know how to make one technique work, then you should be able to earn all the volume points on the exam, if there are any. And then, of course, a big part of our course is about antiderivatives. Antiderivatives are more difficult to find. They're not intuitive. And so we spent a lot more time learning techniques about how to find them than we did about finding derivatives back in Calc 1. And actually, we learned how to do substitution in Calc 1, but it's such a key, vital part of what we do that I think you can expect to find it on this exam. And then we learned some new techniques. By parts was the first new one we learned, and then we talked about rational functions. And remember, we talked about proper versus improper. So I paused for a few minutes because a couple students dropped in to talk about homework, but now I'm good to go. I think we're last talking about antiderivatives on the final exam. When I was talking about rational functions, we have a technique for those, partial fractions. There are 4 cases. You remember we never did talk about the 4th case. The final exam will not have anything to do with the 4th case. Could be the 1st, 2nd, or 3rd. I also want to point out the technique we learned there, and that's how to deal with proper versus improper rational functions. And so think about that, go back and review that. The technique partial fractions only works for proper. I mean, you'll think it works for improper, but you'll get a bad answer. All right, continuing on. And I'll probably emphasize this at the end, but remember, we're covering topics that may be on the exam. And under antiderivatives, I did not mention trig substitution. And so I think you can expect no problems dealing with trig substitution on the final exam. I also didn't mention the section in that chapter on powers of trig functions. And with one exception, maybe actually 2 exceptions, those are not going to be on the exam unless they would land under, some technique that already is listed. That is, you don't need to know anything extra. And the exceptions are sine squared. So I want you to know the integral of sine squared, the antiderivative of sine squared theta. And if you know that one, then it's a tiny little change to get cosine squared. So there you go. Other than that, and other than the things that are covered here, some of the sophisticated, I'm not sure if that's the right word, but more detailed things we talked about in that section, not going to be on the exam. All right, and then we had a section on improper integrals. Remember, there were 2 types. The second type, unbounded integrand, is not going to be on the exam, but the first one may be, and that is an unbounded interval. And you can see I wrote the formula there for how we deal with it. And then we had a section on infinite series. We had actually 2 whole chapters. I think it's important for us to know the definition. The last exam, you may remember, there was a question about the sequence of partial sums, and in general, it was not handled very well. That is, there are a lot of points lost. Only maybe 3 or 4 students captured all the points. And so I think you could expect another question on the final exam about the sequence of partial sums. Let me underline it. The words really tell us what's going on. We always use the symbol S sub n. And so take a look at the, and I have another student. I'm pausing. All right, So the sequence of partial sums, I think you could expect a question about it. And then I put next two very important series, geometric series and p-series. And one thing about geometric series is we can actually find the sum when it converges. P-series, we know 100% of the time when they converge and when they diverge. There's no mystery. But never, ever, at least in this course, do we know what the ones that converge, do we know what they converge to? Some of them are known, but it's pretty much beyond the scope of our ability. We would need some more advanced math courses before we could dig into that. So the value that a p-series converges to, we have no knowledge of, but we have 100% perfect knowledge of the power series, sorry, the p-series that converge and the p-series that diverge. And that became really super useful in the comparison tests, as hopefully you know by now. Okay, and then I just put the word test. We have all of these tests. I think I want to include them on the final exam. One student, Kate, sent me a link to a professionally done video that she found really helpful, and so I'll post a link to that on our Foxtail page. And the guy just kind of runs through all the tests we've talked about and then gives you a strategy at the end for how to think about using them. I think on the video I made back when this whole thing started, these online lectures, I listed out 10 different ways we can determine the behavior of a series. Not all of them were tests. Some of them were, the geometric series, which we don't really think of as a test. The p-series is never really called the p-series test. It just tells us the behavior of p-series. But in the end, there are 6 or 7 different tests there. And so take a look at how this particular professor leads you through a strategy, and maybe it could come in handy on your final exam. And then finally, not finally for all, but finally for what's written on the board, I put power series down again. Yeah, I've asked you 2 questions about power series. One of them was on the last exam, and then I followed up with a question on the makeup quiz. And so because I've asked you it twice, maybe the actual detail there, and remember what we learned early on about power series, they had a radius and an interval of convergence. And then we took all of that information and used it to talk about a new topic, which I failed to list at the beginning of this video with the new topics we've covered since the last exam, but let me make no mistake, it is a new topic and it's a very important one. I guarantee you it will be on the final exam, and that is this whole idea of Taylor / Maclaurin series. So what we're looking for here, let me just say in general, we're looking for a power series that converges to a particular function. You can think of it like this. Here's my function f of x, and a power series that looks like some constant plus another constant times x plus another constant times x squared, and so on. And we showed that if I want this function, this series to converge to this function, I need to pick my ANs, let's call them, like this. I need to find the nth derivative. And I'm going to focus on 0. That makes it a Maclaurin series. If it's not at 0, it's a Taylor series, but we'll start with Maclaurin and divide by n factorial. So that's our formula for constructing Maclaurin series. The coefficients have to have that pattern. So for example, if I take a function and what I figure out is that when I evaluate its derivatives at 0, I get n minus 1 factorial. I think there is a function like that, but I don't really care what it is. I'm just saying, suppose we took a function, we analyze the derivatives, and we realize that when you plug in 0, you get n minus 1 factorial. Then the coefficients, the derivative evaluated at 0, n minus 1 factorial, and our formula has an n factorial built in. And notice then, we can cancel, and so we say, well, the coefficients just need to be 1 over n. This n minus 1 factorial has all of the factors, 1 through n minus 1. This has all of those, and one more, n. So all but the n cancel, and we get 1 over n, and that's how I could construct my Maclaurin series. And again, because I'm plugging in 0, that makes it a Maclaurin. All right. And then there are certain functions whose Maclaurin series are more important. Remember I said these series were constructed a couple hundred years ago to help people do what was otherwise complicated arithmetic with no calculators available. And that's what Taylor and Maclaurin were working on in all of their contemporaries, trying to find a way to make arithmetic doable, not just easy, but doable. And then, of course, calculators came along, and we no longer need them anymore to make arithmetic easy. But along the way, the 200 years since, because mathematicians, scientists knew about these series, they found ways to use them. And the ones that they use the most have survived and are listed in calculus books like your calculus book. And so on page 740 in the textbook, we have a summary of the important, some of them. I guess the important ones for this exam are all listed there. Important, I think they're all Maclaurin series on page 740. I didn't write all, so that's good. I mean, there could be some others. And let me say, ignore, as far as this exam is concerned, the last 3. We didn't talk about them. We're not going to talk about them. But the ones above that can pay attention, because the Taylor-Maclaurin series is a power series. Then every single one of them has a radius of convergence and an interval of convergence. Okay, and on page 740 to the right, you'll see that information conveyed in one fashion or another. Let me just glance at page 740. Yeah, they don't say R equals, but they tell you, for example, here's the very first one. 1 over 1 minus x equals 1 plus x squared. It's a geometric series. In sigma form, we can write it x to the n equals 0 to infinity. And it converges if the absolute value is x is less than 1. That's the way it's written in the book. I see this thing over here, and I say, okay, r equals 1. The radius of convergence is 1. The interval, I think it's pretty clear that if x is 1 or minus 1, the series is going to diverge. And so the interval would just be the open interval minus 1 to 1. Okay, so they're all listed like that. I don't see a single one where it says R equals. And then they have like the most important, here's the single most important Maclaurin series. It's the one for e to the x. Let me write out all the factorials, even though we could simplify them. I'll write it both ways maybe. You need to get up to the third one before the factorial does anything. And now let's clean it up. 1 plus x plus 1/2 x squared plus 1 over 3 factorial. First 2 factorial is 2, 1 factorial is 1, 0 factorial is 1, so the constant term is 1. X cubed plus so on. It converges for all x. It's kind of a miracle. It's because we have this factorial. In the denominator. We can write it in sigma form. N equals 0 to infinity, x to the power n divided by n factorial. And it converges for all x. That series equals e to the x for all x. Okay. The next most important ones are the ones for sine and cosine, both listed on page 740, because every other derivative of sine or cosine evaluated at 0 is 0, then half the terms drop out. For example, cosine, it has no odd powered terms. The coefficient, you get 0 for those every other derivative. So 0 divided by n factorial is 0. And sine, all the even powers drop out. The coefficient is 0 because of that derivative. So on the makeup quiz, I told you in advance that I wanted you to use the Maclaurin series for e to the x. I hope you had it written on your 3x5 card, but there was a lot of confusion. So this series equals that number for every single x value. Pick your favorite x value. I think on the quiz I picked 2. So e squared, if you replace all the x's with 2, you get e squared. Include all the terms. And then on part B, I picked ln 5. Plug it in, ln 5 squared, so on. And you get e to the ln 5, which most of you that saw what was going on recognize as the number 5. And then on part C, I gave you a little warning. The series didn't start at 0. It was missing the first 2 terms. And so if those terms were present, we would know what it converged to. And I believe x was 2 there, so it converged to e squared. But because they're missing, I had to subtract their value off. So I mentioned before that on all those convergence tests, all the things we talked about there, only for the p series, only for the geometric series do we get that it converges and the number that it converges to. All the other tests, they cannot tell us. They can say it converges. They do not have the power to tell us the value it converges to. However, once we start looking at Taylor-Maclaurin, where we're using the function to get our coefficients, now all of a sudden we get to talk about convergence again, the value. Does it converge, does it diverge, and also the value. And of course, we started a little bit before Taylor-Maclaurin by picking on this geometric, because we just knew this fact from our work early in, what was it, chapter 10? And we played some games there. All right. So this kind of went from a final review to a little mini lecture here, but hopefully can put it all together for the final exam. And notice there's a box around this. Maybe most of you probably know Todd Curtis. Maybe you don't know, he won the Professor of the Year this year. So good for him. I'm not surprised. He's awesome. But he has a phrase when he ends up with a major important result. It's box worthy, and he draws a box around it. So here you go. This is box worthy. Like, how do I find the coefficients to get a series that converges to a function? This is how I do it. Do I have another pen? Color. The function tells me, this function tells me what goes there. The factorial is just built into the formula. We have showed that on a previous video. You can go back and look it up, or you can just trust me. All right, so back to the exam. Taylor-Maclaurin series, a super important part of it. To get 100% on the exam, you have to know this. this Boxworthy thing. I'll give you a chance or two to show me that you know what's going on there. And because Taylor-Maclaurin series are power series, then the things we learned about them, the radius, the interval, they come into play for us. We need to know about those things as well. All right, another new topic. Right at the end of 11.2. So more new material for the exam. So we had a power series that converged to a function. So we have like a n x to the n goes from 0 to infinity. And we've established the radius of convergence. I'll just call it r. Then we can differentiate and integrate. And we get a power series for the derivative. So we take the derivative on the left, we take it on the right. The first term is a constant, so its derivative is 0. Let's say we start at 1, and we're going to get a n, sorry, yeah, well, this is fine, times n times x to the n minus 1. So we can differentiate. A n is just a constant. The function on the terms is right here, and the derivative is right there. We can also integrate. N equals 0 to infinity. We have our constant, our coefficient, and then we're going to raise the power by 1, divide by the new power. And on both of these, the interval of convergence, the radius of convergence stays the same. The interval could change. We've looked at some examples like that. But those are some good things to know. And the last thing we talked about is we can do some simple compositions and maintain convergence. And let me give you an idea. We know, I've erased it, it was up here earlier. We know the power series for 1 over 1 minus x, and we could use it to get a power series for 1 over 1, for example, minus 2x. Okay, so we're composing this function we know with the doubling function. And we maintain convergence. This should be convergence. The value of r can change. In fact, it would be exactly cut in half in this example. But I'll let you look at some work, and I'll probably post something about that, like some particular problems later. Now, I think that covers all of the topics that may be included on the exam. The new material, which is Maclaurin, actually the new material we've not been tested over, starts with this differentiation and integration of known power series. Okay, and then we moved into Maclaurin, Taylor series, and then we changed directions completely, polar coordinates and parametric equations. So the new material will be a greater focus on the exam, maybe as much as half, probably not quite half, but because we haven't been quizzed over, except for that one, the third problem on the makeup quiz, it'll be a significant portion of the exam. And then the other topics I listed out will be, you know, maybe they'll be on the exam, maybe not. I don't think you're going to find 5 volume problems or 6 chances to use integration by parts, but you may get a chance to do it. Now, topics not on the exam, let's list those out in black and white here. with all caps. So, improper integrals of the second type. We'll call it type 2. And I'll write in words. Unbounded. The function goes to infinity. Integrand. Trig substitution. Except for specific things mentioned on the review previously, powers of trig functions. All applications of integration that were not listed. For example, arc length of a function. Now, arc length of a parametric curve is a valid exam topic, but arc length of a function, I didn't mention it, and so therefore not on the exam. Work, fluid, force. We might have done surface area. It's in the book. I don't quite remember if we did it. I think we did do it. So the only applications, area and volumes from chapter, what was it, chapter 6? Differential equations, not on the exam. There will be no question on the exam that deals with sequences in the abstract, but I'm not going to write it on the board because for the topics that I have listed, we do need to know some things about sequences, in particular the sequence of partial sums. The divergence test analyzes the sequence of terms that make up the series. And a lot of the tests we're dealing with the terms, which is actually a sequence. So every question that asks about sequences will actually be a question about infinite series. Okay, no, just purely abstract questions about sequences. So I think that was true of the third exam as well. Trying to think if there's any more topics. If there are, you maybe will thinking about them, and you can let me know, and I can post an update. Or if I think of some, I'll post an update. I intend to be generally available Monday, Tuesday next week. Monday's dead day. Look, they're all dead day around here these days. And I'll send some specifics out. And I also will post one more video, probably not today, where I'm just going to pick some random problems, probably out of the book, over the topics that I've said are possibly going to be on the final exam, and I'll just work through them and give you some ideas of what you need to work on, what you need to think about. And remember, I said you could bring 2 3x5 cards with whatever you want to write on it. If you're nervous about those important Maclaurin series, the important ones, I would say right off the bat, e to the x, sine x, and cosine x. You know, just jot them down on your note card. All right, that's it for today. I'll be in touch. Have fun doing calculus.